Ready
Yeah.
to go.
All right. Hi, everyone. Welcome to the department seminar. Today's speaker is Professor Grant Petty, who received his PhD from the University of Washington in 1990. After that, he joined the faculty at Purdue University from 1990 to 2000. And then in 2000, he joined the UW-Madison faculty, where he's worked mainly on NASA-funded research related to remote sensing of global precipitation. More recently, he's branched out into other areas of interest, including but not limited to manned and unmanned airborne atmospheric measurements in the boundary layer. And with that, I'll turn it over to Professor Grant Petty.
Thank you. Well, it's a pleasure to be here today. It's a nice day outside. I can see right out the window and see the sunshine on the trees and the changing colors, so that's kind of nice. What I'm going to try to do here is seamlessly bring up the PowerPoint presentation. Maybe I have to go to full screen mode first here. Hang on. There we go. Is that coming through now?
Yeah, we can see your screen.
Great. Okay. So that's the title of my talk, which you probably already saw in the announcement. Trends in ship-reported oceanic precipitation frequency from 1950 through 2014. And this is an extension of work that I did back in 1994. But in terms of the talk that I'm going to give right now, this is a basic outline of what I'm going to do. First, in order to even talk about previous and current work in relation to ship reports of precipitation, I needed about synoptic format weather reports. And it occurred to me that in order to talk about, if I had to talk about those at all, it might be a worthwhile thing to go ahead and talk about the synoptic format weather reports in general, not just the specific parts that I need, because my impression is that most folks in the US who do meteorology tend to be very familiar with METAR reports, and they may have spent relatively little time looking at synoptic weather reports. And yet synoptic weather reports are very widely used. They have a very long history. They contain a lot of information. They're also a bit hard to read if you're not used to them. So I'll talk about ship and general synoptic format weather reports at the beginning for a little while. Then I'll do a review of work that I did with ship weather reports back in 1994, which is a long time ago. It's hard to believe, but then I'll talk about the methods and the results and the preliminary conclusions from this new work. So just to give you a little perspective, this is a small excerpt of a very long tabulation of different code forms that are authorized by the World Meteorological Organization. And you'll see METAR down here that's primarily associated with airports. But there's also ship and synoptic, or sorry, synoptic and ship reports, which are very similar in many ways, which are reports of surface observations from either a sea station or a fixed land station. And there's a lot of other formats as well that I'm not going to even go into, but the point is that these are kind of on an equal level with METAR reports in terms of a way of describing information. And in many cases, these other formats are the only information available. So the ship synoptic code has been around in something approximating its current form for about 71 years now, going back to 1949. And I think that there was codes that were being used prior to that that contain much of the same information, but things began to get formalized and kind of unified by the WMO back not long after World War II. And it's gone through a couple of evolutions where various codes kind of coexisted for a period of time. And then in 1981, or I should say 82, they got consolidated into one more or less uniform synoptic weather report for ships. Now, just to orient you, if you haven't really been exposed to synoptic weather reports before, they are generally made available every 3 or 6 hours, unlike METAR reports, which are every hour, usually unless there's special observations associated with changing visibility and so on. Some stations only report every 6 hours, other report every 3 hours. The WMO-defined alphanumeric code for both synoptic and ship format weather reports was designed to be very compact and efficient for transmission because the mode of transmission through many decades was teletype, or radio teletype in many cases, which is a very slow way of transmitting data. And so you had to get a lot of information across fairly efficiently without taking a lot of space and time to get them printed out. Something that may not be widely known about the Synoptic report format is that it actually contains more information than METAR. There's 100 distinct codes of present weather. There's 10 distinct codes of past weather. The reports also include things like pressure tendency, and they give explicit information about the low, middle, and high cloud types with 10 different codes in each height range. So you have additional information here that you cannot get normally from a METAR report. There's a lot of fixed land-based synoptic stations. There's a smaller number of commercial and military ships around the globe that are making regular or sporadic synoptic reports, mainly concentrated along shipping routes, but not entirely. And that's important for what I'm doing because I'm trying to look at statistics, not just over shipping routes, but everywhere I can get enough data. The important thing to also know about all these service reports, but especially ship synoptic for the ocean, is that prior to the advent of meteorological satellites, these were the only real source of information about weather over the ocean. There were very few buoys, and then you had ships, and that was your information. That was basically all the information you had regarding where cyclones were, and you know, including things like cyclones over the Gulf of Alaska or what have you. You just had a few clues from a few ships that told you where that low was and what its likely intensity was and what its motion was. And you could try to analyze the position of fronts and so on. When satellites came along, we started by having cloud maps that would allow us to see qualitatively what was going on over the ocean to supplement the information from the surface synoptic reports. But it wasn't until we had founders and data assimilation methods that we began to actually be able to get significant quantitative information beyond just what was being reported by ships. So a key fact is that the synoptic weather reports still are a primary source of surface weather data over much of the globe. Fundamentally, if you want over ocean weather data from ships, that's what you're going to have to look at because they don't provide METARs. And there's also automated weather data sources like buoys and other things that provide data that are using variations on a synoptic format. So here's why I was once an expert on the ship synoptic report format. I say once because things have changed, but I was a Navy weather observer aboard the USS Bellwood in 1978 through 1980. That was my ship right there. I encoded and transmitted hundreds of weather observations in ship synoptic format from the ship. And maybe even more importantly, in terms of familiarity with the synoptic code, I hand plotted literally tens of thousands of regional synoptic reports, both land and ship, on surface maps. And these then had to be hand contoured and analyzed in order to have an updated view of what was going on, say, over the Eastern Pacific, which is where we were usually operating. This is just a couple of random scenes from the ship at the time I was on it. That's me in the top middle and on the upper left-hand corner, and some colleagues of mine. Colleagues, I guess, is not a term we use in the Navy, but fellow sailors, I guess, on the right in the weather office, and so on. The data that we worked with that came from other sources came mostly from radio teletype and from facsimile charts. But I've got a little arrow there pointing to the two radio teletype devices that we had. These were clattering away basically nonstop day and night. And you got a piece of yellow paper that was on a roll that fed out. And as it came out, it was printed with messages that looked like this. Very cryptic looking, not like METAR. You really have a hard time identifying what's going on. You see groups of 5 digits and a few identifying indicators that precede each message in some cases. But very hard to really understand unless you knew what you were looking at and understood the code. Now, the interesting thing is that the way I displayed that on the right there looks exactly the way the stuff came off the teletype in 1978. But this is actually current text messages from just a couple of days ago. I got these on September 26, 2020. That's what the date is for these reports. And so the format and the appearance of these reports has not changed in all those years, going back to 1978, and of course much before 1978 as well. So it's interesting that the SLIC format has, visually at least, not changed in structure or appearance in all those decades. And if you don't know better, you can't really tell that it's any different. It's really, they just preserve the same way of transmitting weather data in kind of raw form now as they did a long time ago, as if it were designed for teletype still. Now there's a very formal and fairly complicated syntactical description of what these synoptic reports look like. I'm not going to go through this. I'm just trying to illustrate that there's very specific rules about how they're structured and how you figure out which code group you're looking at. This is the section that's more likely to be of interest. It contains a section 0 with location and date and time and a couple of other things, and then a second section which is more the basic meteorological data, which is also common to land stations as well. I'm going to go through this fairly quickly, but just to show you what is in this, if you know what to look for, we've got the station key, which is either a 5-digit code for a land station. 72 is the first 2 digits of any U.S. station, or if it's a ship, you've got a 99 followed by latitude and longitude. You've got the lowest cloud height and visibility. You've got the total cloud coverage in octaves and the wind speed and direction. Temperature and dew point in degrees Celsius to the nearest tenth of a degree. Sea level pressure to the nearest tenth of a hectopascal. Pressure tendency over the previous 3 hours. Present weather and past weather. Actually, they give 2 past weather codes, a W1 and W2. We're going to be concerned with the present shortly. And then fairly detailed cloud information, including the codes for these different cloud types at the low, middle, and high levels, along with the coverage by the low and mid clouds, which are primarily of interest to aviators. So here's an example of an actual set of synoptic reports taken from land stations, again, on what was the 26th of September, Sunday, I think. So just Sunday at 00Z, or Saturday afternoon at 00Z. And the highlighted portions here are the 5-digit identifiers. And if you happen to know that Green Bay, for example, is 72645, then you see that that's the report we're getting at that time for Green Bay. And so I'll highlight that and single it out. And we can compare that then with the METAR report, which came out at exactly the same time using the same information, but just encoded in a different way. Now, of course, the identifier is different because the METAR uses the aviation style identifiers KGRB, whereas the synoptic report uses the WMO assigned ID of 72645. But if you know what to look for, you can find the same information. There's the wind speed and direction. There's the 66 is a code for the visibility, and it turns out in this case to be 10 statute miles. There's the number of octaves of cloud coverage. It says clear, so it's 0 for the cloud coverage in the synoptic reports. We've got the dew point, or sorry, the temperature, the dew point. We've got the sea level pressure. I guess that's it for this specific report. There's not a lot of detail beyond that I want to get into. Just to reiterate, there's information in here that MET reports don't contain that the synoptic reports do contain. These styles, these station models are what I plotted by hand when I was doing weather maps in the Navy, and I still like them better because they're more informative. We have the cloud information at 3 levels if there's clouds. We've got some information about the lowest cloud layer, the height and the percent coverage, or the number of octaves covered by those low clouds. We've got the pressure tendency, which in this case is showing that it's gone down 2.8 hectopascals over the last 3 hours, and it's been a steady decrease. And we've got 2 codes for past weather. So apparently there was past rain, and then there's another condition that doesn't mean weather. And the present weather may look like what you get when people plot METAR reports, but again, we've got a lot more codes to work with than what you normally get from just looking at the METAR codes. So now let's look at a ship report. And this is very similar in most respects. There's the identifier. I don't know what that specific identifier means in this case. Here's the location. It turns out to be located just off the coast of Japan. I found that by looking it up on a map. And if I were plotting this, I would start by making a circle of that location and put the indicator for the station, or the ship in this case. Then I would add the winds, and I would add the cloud amount. And the present weather would go right to the left there, which in this case is a code 25 indicating showers of rain during the preceding hour, but not at the time of observation. So you're basically saying it rained over the last, I believe it was an hour, but it's not currently raining. And then we put in the temperature and dew point, the visibility, which in this case is a code for a certain visibility. I don't remember what 97 exactly means. And the sea level pressure. And the cloud layers, in this case, the top two are missing, so there's nothing there except M's. And the pressure tendency and the past weather. And there's other things that can go in there as well, like sea surface temperature, sea state, and other variables that are normally plotted when they're available. I didn't even look very hard to see if they're in this report or not. So that's the crash course in the Synoptic code. What I want to do now is focus on just one element of it, and that's this present weather code, this WW code, which is the way it's described in the syntactical description. In this case, as I said, that's a 25, which means shower rain during the preceding hour. The rest of this talk is about deriving climatological information from that single element of routine synoptic weather reports. Now I'm going to stop because I think I heard a ding in the chat, or maybe not. And I don't, so I was mishearing. All right, I'll keep going. So the rest of the talk is about taking that single element of synoptic weather, present weather, and turning it into something climatological over a longer period of time. Now there's a complication that didn't occur in the synoptic code until after I'd left the Navy, and it took me a while to realize that this change had been made. But in 1982, a rule change allowed synoptic reports to omit the present weather code entirely if there was no significant weather report. So there's two cases. Some stations, especially automated stations, simply never report the present weather. Some stations simply omit it when it's not significant. If you want to do statistics, you have to know which one is the case for a given report. Fortunately, it turns out that they've added another code, which is called IX, which is basically an indicator that tells you, in the case of different standard or automatic stations, whether or not the present weather code was omitted because they simply never report it, or it's not available, or because it's not significant. And so that allows you to, fortunately, distill the data down to something where you have a pretty clear idea of whether or not there was significant weather report, and not simply that it was not being reported at all. All right, let me drill down a little bit into these present weather codes because they're central to everything that happens going forward, although for the later work that I do, I haven't utilized all the detailed information that's in here. As I said, there's 100 present weather codes starting with 00 and going up through 99. And these are grouped according to different categories of phenomena. The 00 through 49 are all associated with no precipitation station at the time of the observation. Now, I didn't break it out here, but the 30s, for example, cover things like blowing spray, or if you're over land, blowing dust or blowing sand. The 40s cover various kinds of fog, but they're all non-precipitating. Starting with, I guess I do have that broken out here in these two lines right here. Sorry, that isn't there. But then starting with code 50, we're dealing exclusively with precipitation at the station at the time of observation. So the 60s are basically rain. The 70s are basically solid precipitation, mostly snow, but there's also things like snow rains and snow pellets and things like that in there. 80s are exclusively associated with showers of precipitation, whether frozen or liquid. And the 90s are generally associated with current thunderstorms. So we have a lot of detailed information as to what's going on if you know which code you're looking at. Just to break it down or show how these work for the drizzle categories, 50 through 59, we've got intermittent or continuous, slight, moderate, and heavy. We've got freezing, moderate, and heavy, drizzle combined with rain, drizzle and rain, moderate and heavy. So these are all fine distinctions that are being made by those different codes. Same kinds of things exist for the rain codes and the solid precipitation and the showery precipitation. We got everything from rain showers that are slight to violent, and snow showers of or showers of snow pellets and small hail, with or without rain, slight or heavy, moderate and heavy, whatever. So it's a rather finely grained discrimination. And interestingly, at one point in my life, I had most of this table memorized, except for the ones that were very rarely used, like snow grains or diamond dust. I didn't use those enough to really remember them, but I could look them up easily enough if I needed them. And then the thunderstorms, of course, as well, including the 99, which is heavy thunderstorm or severe thunderstorm with hail at the time of observation. That's kind of the worst. Here's what all the little graphical symbols look like for those 100 codes. And so if you were plotting these by hand, you had to remember all of these to be quick about writing everything down. As soon as you saw the present weather code, you simply went over and you drew in the little dots for it. And it didn't take long before people who did this plotting were, again, very familiar with all these symbols, as long as it was a symbol or a present weather code you encountered often enough to get familiar with it. Now, the question is, how are these present weather codes determined? And this is where we deviate quite a bit from the usual concept of making measurements, where you measure something and you quantify it. You probably have some kind of calibration, and then you report it with error bars if you're doing things in a rigorous way. It's very different in the case of the present weather codes, because a human observer simply goes outside and subjectively assesses the sky cover, the visibility, and the present weather. There's a whole volume of written rules from the WMO that describe or prescribe which present weather codes apply to a particular situation, and observers learn most of these common ones by heart. And there's a precedence in that a higher numerical code takes precedent over anything lower. So if you have more than one thing going on that could warrant a present weather code, you take the one that's higher and having higher precedence. And so generally, rain takes precedence over fog, thunderstorms take precedence over rain, and what have you. Now, this assessment generally cannot be automated. There's not really any way for a non-human observer to make these 99 distinctions. And so to date, at least, automated stations generally do not provide a present weather code as part of a synoptic report. So we're relying pretty much entirely on human observers, and the same is also true for cloud amount. Ceilometers will tell you what the cloud height is, but they don't do a very good job of telling you what the cloud amount is automatically. So my thesis, which is the basis for what came next, or what comes next, is that by tabulating the occurrence of different present weather codes within your geographic box over a longer period of time, you can determine the climatological frequency of occurrence of precipitation of a given qualitative intensity and the climatological fraction of precipitation events exhibiting particular characteristics. Now, the historical context is that there had already been a number of efforts to derive climatological maps of monthly precipitation amount by taking these shipboard reports and trying to calibrate them in terms of an average intensity. And so there were maps of rainfall, monthly rainfall, climatological monthly rainfall over the oceans, starting with Tucker and then in the early 60s. And then the latest one that I think was still done was Legates and Wilmot 1990, where they're essentially trying to use ship reports to derive how much rainfall is falling over the oceans, because there was literally no other information. The ships have no gauges, so there's no way to directly measure the amount that's falling, or even to calibrate the quality of descriptors. And descriptors, moderate, heavy, etc., are extremely subjective. Somebody who lives in the tropics probably has a different idea of what heavy rainfall is than somebody who lives in, say, Alaska. And so heavy to an Alaskan might be very different than heavy for somebody in a warmer, more tropical or convective climate. So it's really difficult to be confident of calibrating these descriptive weather codes in terms of an amount of rainfall. And yet, again, that was all we had. There was no other way to get it at the time, and so that's what people try to do. Now, the flip side is that the determination of whether or not it is raining or snowing is not ambiguous. If you go outside, you generally know whether it's raining or snowing or not. And so that determination, it might be subjective, but it's not ambiguous, and it's likely very robust. So my thinking was that I should just take these robust indications of precipitation character and occurrence and see what I can do with them. And I'll talk about my motivation for that as a bit of a footnote, but I came out with a paper in 1995 in BAMS, which was looking at the global precipitation, the frequencies and characteristics of global oceanic precipitation from these shipboard weather reports. I'll give a quick overview of what that was about. And before I do, let me just check and see if another chat thing came up, because I heard a ding. But no, I guess that's just my bell ringing for email or something. Okay. So I had 34 years that I got from the Comprehensive Ocean Atmosphere Dataset called COADS. And at that time, it was available only up through 1991. It always takes them a couple of years to get caught up with the present time. And I didn't want to go back earlier than 1958 because there were some ambiguities about reporting prior to that that made me worry that it might be hard to interpret what's there. So I kind of subjectively chose 1958 as my starting point, and then I took that forward to as far as I could go, which at the time gave me 34 years worth of data. Now, the COAS data set is not itself in the Synoptic format. It's a uniform digital format for both manned and unmanned maritime data sources, including the ship Synoptic reports. But what they've done, they've taken the contents of those Synoptic reports and kind of massaged it into this binary or digital format, including the present weather report their present weather code that I wanted. But it's the same. The COADS version is the same for all data sources. Now, what I did next was I thought we got 100 codes to work with, or we've got about, I guess it would be more like 50 codes to work with for precipitation. That's a bit much to try to break down in a very granular way. So why don't we group them into different categories? And the three ways of grouping them that I could think of was qualitative intensity, phase, and character. So the intensity, low, light, medium, or moderate or heavy. Phase would be liquid, frozen, or mixed phase. And character could be things like continuous or showery or convective. And then from those categories of reports, I could calculate ratios, including the ratio of any kind of precipitation of a given intensity to all reports. Or I could look at subsets of the precipitation relative to all precipitation, so I could see what fraction, for example, is frozen or convective or what have you. So here's what that looks like. I've got the intensity classes, and I've got an indeterminate, extremely light, which I basically mean drizzle intensity, light, moderate to heavy, because they didn't usually distinguish between moderate and heavy for many of the codes. Then I had phase classes are indeterminate, liquid, frozen, or snow, or transition. And then character classes were things like steady or intermittent, which would imply more stratiform precipitation, showery, or then in some cases, the code was indicating that you had something like strong convection or a thunderstorm going on. And then when you considered the various combinations that existed of these three different categories, you could get these groups where, for example, all of these codes right here, 13, 17, 18, 19, 20, and 29, all imply indeterminate intensity, indeterminate phase, but clearly associated with strong convection or thunderstorm. Well, what might that be? 13 is distant lightning. 17 is what they call a squall, although they never really defined what a squall was. Squall seen at the station. I don't remember offhand what 18 is. 19, I think, is a water spout. 27 is, I think, past showers over the previous 3 hours. 29 is past thunderstorms over the past 3 hours. And if you go to rain, for example, let's look at, let's look at drizzle. So we got several different categories of drizzle, which all basically imply light intensity, liquid phase, and steady or intermittent. So once you group them that way, you've got fewer categories to work with, and you can start doing statistics on those categories to see which are showing up more frequently than others. So this is scanned right out of the original paper that I published. So it's black and white. This is back before color was very easy to do in a journal article without spending thousands of dollars and doing a lot of work. So I did everything in black and white. That's how you know this is 1995 or 1995 and not the current situation. But this is just a raw depiction of the sample counts for March, April, May up here, June, July, August, September, October, November, and December, January, February. And of course, they look mostly the same. You see the major ship tracks between like the Panama Canal and other locations. Heaviest traffic is up in the northern Atlantic and North Pacific. And this is a logarithm scale, so we're talking here about over 1,000 ship reports per 2.5 degree box for the 3-month period over the 34-year record. Whereas when you get to the southern hemisphere, you can see that we're falling down into the tens of reports or even fewer per 2.5 degree box over 34 years. And so you realize the data gets quite sparse. And it gets extremely sparse in the southern hemisphere, the southern hemisphere winter, when there's not many ships tooling around down here at all. So the statistics of looking at what's going on gets very spotty once you get into the more remote areas of the ocean where you don't have shipping lanes. You might have a few research vessels, you might have a few military vessels, but you don't have a lot of commercial merchant ships. But nevertheless, you can set a threshold on how many reports you have to do something interesting with it, and start looking at things like the instantaneous probability of local precipitation for each of the 4 seasons. And we see that, for example, off the coast of Africa, North Africa, we're getting percentages less than we're getting less than 1% occurrence of precipitation in that zone. Whereas maybe in North Pacific, you might be seeing 10% or even more. And you go to the southern hemisphere and you don't have a lot of reports to work with, but at least on a fractional basis, we're talking 10, 15, sometimes even 20% of those reports are indicating some kind of precipitation occurring at the time of the observation. And again, southern hemisphere, the southern oceans in their wintertime, you get nothing at all. There's just not enough ship reports to really tell you anything. You can look at the frequency of deep convection in the vicinity of the ship, and you get a slightly different patterns. You see the ITCZ very clearly. You see things going on in the Indian Ocean. It's a different distribution, and you don't see nearly as much going up into high latitudes as we saw on this plot. This one is looking at the occurrence of drizzle intensity precipitation as a fraction of all precipitation. So it's conditioned on there being precipitation. And we see some areas that stand out, like off the coast of North America, the west coast of North America during the summer months, where there's a pretty high frequency. About 50% of the reports of precipitation are going to be ascribed to drizzle and not to something of higher intensity like rain. And that you find the high drizzle occurrence occurring mainly in these subtropical zones and the subtropical highs off the western coasts of the continents. And there's, that's a pretty general thing we can observe there. But in short, this gives an example of how we can tease apart the reports we're getting to see climatologically significant distributions of precipitation. Snow fraction, this is basically the fraction of frozen precipitation, and there's no surprises here. Basically, as you get to high latitudes, you're looking predominantly at snow, and up here in very high latitudes as well. And if you go to the summer months, we have enough ship reports to see that even during their summer, we're still getting a lot of snowfall as we get close to Antarctica. This one's interesting because it's looking at the occurrence of thunderstorms, unambiguous thunderstorms in the vicinity of the ship as a fraction of all non-drizzle intensity precipitation. And I thought this was very striking because it's highlighting that we're seeing zones of high thunderstorm occurrence in the ocean regions that are generally not very far away from the continents. And this is true off Africa and off North America and in the Indian Ocean and so on. But once you get out to the middle of the Pacific, for example, you just don't see thunderstorms. It's just not common to have thunderstorms reported as part of even the deep tropical convection you find in the ITCZ. So this distribution of thunderstorm occurrence was a very striking feature, and to my knowledge, up to this point, nobody had ever actually mapped this out before because nobody had looked at ship reports in this way, and there wasn't really much else to look at that time. Now, subsequently, we had the TRIM satellite that got launched in 1997 that had it had a lightning, LIS is what it was called, lightning imaging. I forget exactly what it stands for. I just called it the LIS. And Bocipio et al. 2000 came out with what I believe was probably the first map of the geographic distribution of lightning observations from this satellite. It was orbiting primarily over the tropics and subtropics. And interestingly enough, if you compare that with the map that I have for occurrence and go back and forth, you can see that they line up pretty nicely. So the satellite data in this case seems to corroborate pretty well the occurrence of thunderstorm activity reported by ships, which suggests that it's a real feature and not just some weird observing bias by the people on the ships going outside and seeing what's going on. So that was very encouraging. But this satellite work came about after I had looked at the ship reports and seen these features based on just subjective human observations. So just a quick footnote to this 1995 study that I did. There was actually an ulterior motive that I had in doing the study. I was involved, and still am to a degree, in working with satellite rainfall retrievals over the ocean. And a lot of this work began when I was a graduate student, and that's what I pretty much specialized in through the early 1990s and beyond, actually. And back in the early 1990s, there was several different groups around the world in different countries, in the UK, in the United States. Even with the United States, there were probably 3 or 4 different groups doing stuff, all trying to retrieve ocean rainfall from passive microwave imagery from the SMI, which flew starting in 1987 on a DMSB satellite. And there was a first precipitation intercomparison project called PIP-1, which basically looked at every participating algorithm's map of precipitation over the ocean primarily, but there was a few algorithms that were trying to do over land at that time as well. And so the goal was to look at what each one was doing and get some insight into how well they were converging on a common answer to how much rainfall there is out there. And the primary emphasis was on the amount of precipitation, but obviously one of the things also look at is how much precipitation is occurring, how often precipitation is occurring, and that's in a way a more robust thing that you can look at. So my algorithm, well, let me back up and say that there was 10 participating algorithms, and most of them, all but one actually, showed a rapid fall off in precipitation frequency at higher latitudes, falling off to like 3, 4, 5% maybe. Whereas mine, which was in the mix, showed an increase, peaking at about 15 to 20% as we got to, say, the Antarctic coast or the very far northern Atlantic. Naturally, my algorithm was regarded as an outlier, and the implication in the write-ups that I saw of the PIP-1 exercise was, well, mine is an outlier and it's probably wrong. And naturally, I took that as a bit of a challenge because I had some confidence that what I was doing was a little more sensitive to light precipitation and shallow precipitation than what other folks were doing. So I thought I need to get out and find a way to validate this and try to find independent information as to what's going on. Well, there was no direct validation at the time for ocean precipitation frequency or even amount. There's a few tropical atolls that were able to measure rainfall on daily and monthly levels, but not instantaneous, and there was nothing really outside the tropics to independently verify precipitation at all. So at that point, I realized, well, I was a shipboard weather observer. I realized there's ships out there where the observer is looking at whether rainfall is occurring. Let's see if I can get the data and analyze from these reports how frequently precipitation is occurring. So there's a follow-on paper in 1997 that I did where I explicitly compared the 10 algorithms with the ship-based observations. And the end result of that was basically to show that those 9 other algorithms actually badly underestimated the occurrence of precipitation latitudes, and one didn't. So fast forward now to 2009. A paper came out in GRL. Tristan was one of the authors on that, and Todd Ellis, I think, was a student working with Tristan at the time. And the question was asked, how often does it rain over the global oceans? The perspective from CloudSat. And the thing that CloudSat has going for it is that it has a much higher sensitivity to very, very light precipitation. So it's a much more robust indicator of the occurrence or lack of occurrence of precipitation. And what they found, just pulling from the concluding remarks, is that the CloudSat radar observations compare favorably to concurrent ship-based and island-based observations of the occurrence of precipitation. So it largely corroborated the very high precipitation frequencies that I found at those high latitudes, and that was gratifying because this was truly the first independent validation of that analysis. Now let's fast forward another 10 years to 2019. specifically November 2019. Tristan Lecuyer gave the departmental seminar and talked about atmospheric and oceanic, we talked about global precipitation trends and whether they could be observable in our lifetime. And the reference there was to CloudSat observation precipitation. And how long does the record have to be in order for trends to be statistically significant based on what's observed over the available record? When I saw the talk, I was very intrigued by what he was talking about, because at that point, the idea was that CloudSat is getting close to being able to observe trends in precipitation frequency, but it's not quite there yet. But then I had kind of a brilliant, not brilliant, but the bright idea that maybe I could go back and revisit the ship reports and see whether there's an opportunity to do what I had not done before, which was to look at trends. So I asked myself the question, can I take the previous analysis of ship reports and look at precipitation frequency trends over time? Now, it may sound like an obvious thing to do, but it's not quite as easy, because there's a couple of really important concerns. One is sample size. Within each grid box, the sample size suffers when you subdivide by time. And so if you start with an aggregation over several decades and you have, say, let's say you have 1,000 reports over 50 years, just to take round numbers. When you divide that into 50 individual years, you're down to only 20 reports for each of the years, and you start to have very important statistical uncertainties in the ratios that you calculate from your samples. And that's, of course, especially problematic at locations for which the sample size is already marginal, such as the Southern Oceans. Less so along the ship tracks, where you might be starting with 10,000 reports within a box, in which case you're not going to be as affected by that. But it's a super important problem to deal with, especially with the regions of the area the regions of the globe where you don't have a lot of ships most of the time. The second thing that concerns me, and still concerns me because it's very hard to get into this, or to really dig deep into it and document what's going on, is that over time there have been changes in reporting procedures and habits that might affect the reported trends in precipitation. And certainly when you get into things like reporting categories of precipitation, not only formal procedures, but also just habits, what people are thinking of when they do their report, whether they're looking at a smartphone while they're out taking their observation or whatever, might affect how frequently different reports show up. Or even familiarity with the different codes might change over time depending on training. I still worry about that potential source of bias in any trend that I look at, but nevertheless, it can't hurt to just dive in and see what comes out. So I went to an updated data set. It's basically an extension or a revision, an update of the original COAS data set. It's now called ICOADS, the International Comprehensive Ocean Atmospheric Data Set, ICOADS Release 3. And it's available through 2014. I'm not quite sure why we're still 6 years behind on that, because I'd love to be able to take it another couple of years, maybe 4 years or so beyond that, but right now I'm stuck at 2014. I went back to my 1958 start date like I used before, so I now have a 57-year record to work with. And from that entire record, I have a total of 117 million manned reports from ships over the ocean, of which about 96 million qualified in terms of being sufficiently, having unambiguous information that present weather was being reported and so on. I had to throw out the ones where I didn't think that present weather was being reported at all. This graph really shows the inhomogeneity over time of these reports. The top blue curve is the total number of reports from the record. The red curve, or the orange curve, I guess that's orange, is the number of reports that include the present weather code. And you'll see that it kind of tracks the total reports up till about 1982 when they changed the rules, and it drops down quite a bit. And then it kind of recovers a bit, and then it drops down again relative to the number of total reports. So the number of reports that came in went up again sharply for some reason, but the number of reports that had present weather did not. They continue to kind of trail off, so that now we're down to about a third of the total ship reports, including present weather. I also looked at cloud cover because I figured that if somebody is observing present weather, they're also observing cloud cover and vice versa, so that might be a good indicator. And that's the green curve right here. And you can say that continues to track the manned or the total ship reports up to about 1990, 1995 or so, and then falls off, and then tends to track the present weather codes after that. So in short, there's a lot of things changing over time that make you worry that you're going to have problems interpreting things in terms of trends. But if you take, for example, all the ships that reported a code greater than 30, which is or equal to or greater than 30, which is everything from blowing spray to fog to precipitation, and look at that as a fraction of weather reports where the cloud cover is non-missing, it's a fairly steady fraction of around 10% with some fluctuations up and down. And if you limit it just to precipitating reports, it's again a fairly steady fraction globally with a few fluctuations up and down. And so these plots here suggest to me that once you make the correction for who's reporting cloud cover and all of that, you might actually have something which is a little bit more robust and you can rely on to look at more regional trends. So here's the map from the 57 years of the number of reports over 5-degree boxes. I made the box bigger than 2.5 degrees, which is what I used in 1994. Increased my sample size. We got a logarithmic scale going from 100 up to 1,000,000 basically per 5-degree box over the 57 years. These dashed lines indicate regions that I single out later on. I won't get into that yet, but you can see that we range from anywhere, hundreds of thousands of reports with the North Atlantic per 5-degree box down to a few hundred in many locations in the southern oceans. The more important statistic is really the number of reports of precipitation, because that's what's going to drive the statistical confidence that we have in the ratios that we calculate for various things. And of course, the numbers overall go down quite a bit, but in the northern Atlantic, we're still getting over 100,000 or 10,000 or tens of thousands of reports per 5-degree box, and the same over the northern Pacific. As you get into the drier zones, of course, the number of reports go down, and so the sampling is going to become very poor. Even if you have a lot of ships there, here's a ship track, so it improves a little bit right there. But ultimately, what you want to see is what's the ratio between these previous two. There's the total, there's the number of reports of precipitation. The ratio of those two is this plot right here. And it actually doesn't look too bad. You can see the ITCZ, you can see the storm tracks in the North Atlantic and Pacific, you can see the SPCZ, you can see, again, very high frequencies of precipitation in the southern oceans. And of course, you see the dry zones as well. So overall, the percent precipitating doesn't look too bad, and it looks very similar to what I had in 1995, except it's in color. It's a little nicer to look at. At this point, what I did then was for each grid box, and these were overlapping grid boxes, again, to try to get some kind of statistical robustness to the results, I calculated linear trends over the 57 years. And that's this plot right here. This is the percent change per decade, ranging from 0 to plus or minus about 12% per decade. And the striking thing about this plot to me is that most of the temperate zones and tropical zones show a rather pronounced positive trend in total precipitation frequency. This is annual. We're taking just all the ships for a given year, we're throwing them into one pot, we're not discriminating by season or month or anything else, but we're doing it geographically, and these are the maps that fall out. We get a fairly robust apparent signal of increasing frequency, with a few exceptions, primarily in the northwestern Pacific, far northern Atlantic, and some portions of the southern oceans, where the trend is negative, and in some cases significantly negative, like 5% or so per decade. So I expected a much noisier plot. I expected it would be driven much more by sampling statistics, but clearly sampling statistics cannot give rise to these very geographically coherent pictures of the trends. Now down here in the southern oceans, we're getting sampling noise. That's why things look a lot spottier there. But in the northern, more heavily trafficked areas, it's a pretty smooth feel we're getting out of that, which I think is rather striking. I did break it up then by region, where I chose, I'm going to call them representative areas, but they were chosen subjectively And I tried to balance the desire to get a diversity of different parts of the ocean against the desire to have an adequate sample so that we're dealing with robust statistics. So I tried to stay near the shipping lanes, and I tried to stay in places where I knew there was a lot of ships for various reasons, but also still look at places where things might be interesting, like the Western Pacific, the Southern Pacific convergence zone, and places like that. So there's nothing magical about these regions. Because I thought they were interesting because they tended to be associated with fairly dramatic trends, especially this one right here, for example, where the trend is strongly positive, but that's kind of representative of a broader zone of positive trend. In graphical form, this is what the time series look like for each of those. And I'm not going to go through this in detail because I can't really pull out specific features that I think are really worth highlighting. They're kind of noisy, but the trends still are relatively clear. I'll point out that if you look at the bottom of each plot, you'll see a dash line. And those dash lines indicate the magnitude of the expected random error just due to the sample size. And so in some cases, you can see that sample error is larger because there is fewer samples, and it may vary over time. And you can compare that expected sample area as a standard deviation with the magnitude of the fluctuations about the trend line. And you see that the individual fluctuations aren't that out of step with what we think of for the sampling error, but the overall trends are fairly robust. And in some places where the sampling error is fairly small, you can see the noise is not that great, but this is over the Sea of Okhotsk off of Russia, north of Japan, and is a downward trend that looks pretty robust. And wherever you look, you see things that look kind of like this. The only exception is that over the Gulf of Alaska, or the region I picked, it's pretty steady, unlike the other places. And this region was picked in part because we had ocean ship Papa at the time that had reports that I could look at individually and compare versus all the ships that were passing through that region. And it's reporting higher percentages. It's hard to see here, but there's actually a correlation in this time segment. The correlation goes to pieces during the earlier years. I don't know why. I don't know what to make of this intercomparison, but at least in this instance, we're seeing not much of a trend, whereas the other regions that were picked out, we do. The question then becomes, we're looking at annual ratios of the reports. Is it possible that we're seeing changes in the shipping patterns over time, in that they're sampling different times of year differently over time because of maybe changing ability to deal with rough weather, what have you? So I decided as a next step for these same regions to break it out by season. And these results are expressed in tabular form here. This column right here is just the same trends that we saw in the previous plot. So if you compare these trends in percent per decade with these plots, you'll get the same numbers. Then we also have it broken out by the 4 seasons. Gulf of Alaska is a special case because the trend overall was quite flat, and so we see positive and negative fluctuations of 0 for the 4 different seasons. But for every other case, say the North Atlantic zone, we have negative trends of very comparable magnitudes across the seasons. Over the Gulf of Mexico, positive trends of fairly comparable magnitudes across the seasons. Tropical Atlantic, positive trends, fairly strong positive trends across the board, around 10% plus or minus. Western Tropical Pacific, a smaller positive trend, but still all positive. The SPCZ, all negative. Eurasian Sea, all positive. And the Southeast Atlantic, all strongly positive in this case. And so we not only have the geographic coherence that we saw previously in the map, we also have what looks like seasonal coherence in that these trends have the same approximate size and magnitude irrespective of season. Now, the magnitudes of the rainfall amount within those seasons varies quite a bit because some areas have a very strong seasonal cycle, but as a trend in percent, that percentage trend seems to be fairly robust. So some comments on significance. In principle, you can report the statistical significance of the computed trends by assigning statistical uncertainties to each year's value. And as I alluded, but didn't really go into details, that can be calculated as the total fraction of precipitation divided by the square root of the number of precipitating reports. And then you can use those uncertainties to calculate the significance in the trend. But the statistical uncertainty, in my opinion, is swamped by other as yet unquantifiable uncertainties in a specific case. The compelling evidence that I think that these are statistically significant trends is, again, the strong coherence in space, the strong coherence across seasons. But we can't rule out that there are other biases that I haven't identified yet that relate somehow to reporting shifts in shipping patterns or whatever. And it's a major can of worms to dig into that and try to figure out what's going on, especially since the historical documentation for synoptic weather reports is not very detailed and kind of hard to track down. So, preliminary conclusions. The analysis of 57 years of shipboard synoptic reports of precipitation occurrence seems to identify large positive trends over most of the tropical and subtropical oceans, with negative trends over more limited areas, especially at higher latitudes. If they are real, and by real I mean in the sense of meteorological, then the positive trends might be consistent with the acceleration of the hydrological cycle and other mechanisms associated with global warming, as discussed, for example, by Chu et al. In 2012. Negative trends at higher latitudes, and this is speculation on my part. I'm not a physicist. I'm not a climatologist. Those negative trends might somehow be the result of reduced temperature gradients and contrasts, and might reflect reduced baroclinicity or reduced open cell convective precipitation when you get cold air masses moving over water, which is a lot of the showery precipitation at higher latitudes. It's interesting that the largest contiguous area of negative overall trend appears where wintertime precipitation is often frozen, and so it would be interesting to try to tease out to what extent those negative trends are specifically in the context of frozen precipitation, or whether they're across both phases of precipitation. All of this stuff has been written up and submitted to GRL. It's under review right now. I have a non-reviewed manuscript preprint, which is available at this link right here if anybody's interested. Future work would be to try to break this down and look at trends separately for frozen, liquid, and or non-drizzle intensity precipitation. Keeping in mind again that as soon as you get more granular with your statistics you're looking at, the statistics can become very poor very quickly. So there's a limit to how far you can take this. If you're looking at something which is relatively rare to begin with, then you're going to be really rare if you break it down further. I think it's important to look at the relationship between the trends that are observed here and what their relationship is to known interannual and interdecadal climate variations like ENSO, the Pacific decadal oscillation, the Atlantic multi-decadal oscillation. That's, I think, an area that some work is needed to understand what portion of those trends might be related to those oscillations. It's not my subject area. I would have to work with somebody on that. What I have been a little excited about in talking with Tristan and having seen his talk is that with CloudSat having been operated now since June of 2006, we can start to take the, at that point, 8-year overlap period, 7.5 years of overlap, and directly compare it with CloudSat observations of precipitation frequency at selected locations, and see if we're seeing similar kinds of things. That overlap period might be too short to look at longer-term trends found over our 57-year data set, but if we can at least validate the interannual variability that's observed by both data sets within that 7.5 years, that might reinforce or weaken confidence in the trend that we're seeing with a longer period of time. Just to acknowledge Tristan for his early helpful feedback on these results, and of course the fact that he inspired me to do this analysis in the first place. This is work that is kind of the final thing I'm doing under an expiring grant under the Precipitation Measurement Project, which is satellite-based, but this is in some way connected. And if you want references to the work that I cited in this talk, you can again find them in the bibliography for the paper in the preprint. And that's all. So I will see if there's any questions at this point. And I see Stephanie. You want to just go ahead and turn on your mic?
Yeah. Hey, Grant. Actually, do you mind pulling up your presentation again?
Sure.
Do you mind going to your slide where you show all of the different trends?
Sure. Let me remind myself how to do that here. That would be this one and this one. It should be up now, right?
I see your,
Yeah, it's up.
yeah, your presentation is up.
That's what
But
you
yeah,
want, right?
this one here, yeah. Okay, so for one thing, this is really interesting and a really cool idea, I think. With regards to the trends, I have kind of a general, I guess, comment and piece of advice to what I'm going to guess is a comment that you're going to get from your viewers with regards to the trends. So for some of these, they look very, very robust, right? Like if you look at the Gulf of Mexico, like that's, some of them are really continuous and they seem to be really clear. But for some of them, like this very center one, which is the West Tropical Pacific, it kind of looks like if you were to split this time series in half, you would get probably a flat line, and then most of it would be driven by kind of the very, very end. So one kind of general piece of advice that I give people working on trends, because people are so particular with trends, and you will probably see that with the reviewers, is to just split your time series in half and calculate the trends for both halves. Just to make sure that, for one thing, that the trend is real and not driven by an outlier or some piece of natural variability that's driving change just in one particular decade, for example. But it also kind of strengthens the fact that some of these are clearly seem very robust, right? Like there's some you see this similar trend all throughout your entire time series. So it just kind of, I guess, something that you could do to help answer your second point in your summary, which was, if these trends are real, based on the data that you have, of course. But this is a really cool idea, and that's just something that can be done to try to kind of assess how whether it's a long-term trend or something more driven by shorter timescale variability.
Yeah, well, I think that's an excellent point. In fact, I don't have the text in front of me, but I believe with respect to either the North Atlantic or the Western Tropical Pacific, or maybe both, I can't remember what I wrote, but in both cases, I believe I'm making the comment in the text that it looks like the trend is flat for a period of time, and then that the trend is dominated by a big jump toward the end of the period. And the same thing is actually true if you look at the North Atlantic as well. It looks pretty flat until about 2000, and it takes a nosedive. So I didn't break it out quantitatively the way you described, but I do believe I made reference in the text to that exact phenomenon, the fact that there's no trend and then there's a big jump, and if you put the two together, you get the combined trend, but that you have to understand in greater detail what's really going on with that. The trouble with TRL is they've got a very strict page limit, and it's hard to fit a lot of stuff. I've already hit the page limit in the draft that I've got, and it's going to be challenging to add new information to that without having to cut other things out. But it's a good point. I think it's really important. And I think that it really is the basis here for doing a much more involved study going forward, probably working with the students to try to tease out in greater detail what's really going on. And maybe I should have called the title of this talk and the paper, for that matter, preliminary trends or preliminary analysis of trends or something, to make clear that we're not claiming to find the complete answer to anything at this point, but we're simply drawing attention to what jumps out at us when we take a first cut at looking at this unique data set, which I don't think is looked at by very many people.
Yeah, that's really cool. It would be really also interesting to see these. I mean, I know you mentioned that you have limited space, but it'd be also really interesting to see these, what these trends look like, what the time series look like for the different seasons, to see if there's a particular season that's dominating, even though you showed similar values, but maybe where you see kind of flatlining and then a trend. Maybe that trend is more robust and throughout the whole thing for a particular season. And more, I don't know, I'm just curious as to, I guess, what they would look like for different seasons. But yeah, this is really interesting. Thank you, Grant.
Yeah, well, thank you for your comment. And I think that what you're suggesting is exactly right. That's what should happen. And again, with the caveat that you have to limit your attention to places where you have enough ship reports to be able to do that kind of breakout and have something which is sort of meaningful to look at. And I think that in these regions, I mostly do. But Again, it takes a little more work to really nail down what the magnitudes of the possible uncertainties are.
Does that mean I'm next in line?
Looks
think
like
so, yes.
who's up next?
Thanks for I'm going to say I'm up next, unless there's any students who want to jump in front of me, because students can always jump in front of me. Okay, I'll just go in. Hopefully a student will check in later. That was super cool. Thanks. And you picked my favorite region. Thank you. The subpolar North Atlantic.
The North Atlantic, okay.
Yeah, subpolar North Atlantic. So that's pretty cool. And I have a potential hypothesis for you to go chase on the subpolar North Atlantic one. It doesn't have to do with the AMO. It has to do with the fact that we think the thermohaline circulation in North Atlantic, so the Atlantic Middle Overturning circulation, is slowing down in the last decade or two, which decreases in the convergence, which cools it off. And then if things are, this is the idea known as the warming hole. So that's the one place due to anthropogenic climate change we're expecting to see a bit of cooling. And so if it's cooler, just by like a Clausius-Clapeyron type argument, you could imagine that, okay, maybe we're going to get less rain because the hydrologic cycle locally is less juicy. That would be my guess. You'd have to look into it more. Maybe we should chat sometime.
So I think that's great, and I actually know about the thermohaline circulation and the reduction in intensity, but I did not think to relate that to what I was looking at here, and so I appreciate your prompting me. I only heard your voice. I didn't see who was talking. Who was that speaking, please?
Oh, it's Elizabeth.
And that's what I thought, but I didn't want to guess because if I got it wrong, somebody would feel insulted.
Okay.
I'm not insulted, but you know that I don't recognize everybody's voice perfectly. But yeah, thanks. I appreciate that comment.
Sure, just a thought. My favorite region. Had to say something.
Hi,
Was
Grant.
there somebody else?
Guess who this is based on the voice?
That's Dan, right?
Nice talk. Enjoyed it very much. I'm struck by at the very beginning your work that you did for BAMS back in the 80s, where you identify these just the climatological regimes, and it seems like there's a real opportunity to link these two, especially in looking at trends, especially drizzle. I'm looking at
that one right there.
drizzle. Look at B at over the North Atlantic and the North Pacific. Where the frequency from drizzle is over 50%, right? So you've got a lot of
frequency relative to all precipitation, is to be clear.
Yeah, but still, I mean,
Yeah.
right, sure. So most of what you're seeing there in those regions, when you're looking at trends in precip occurrence, is drizzle, right?
Yeah, about 50% or so, right?
Yeah, in that season. And that's, I mean, we just heard from Marlene Fiore about changes in sulfate aerosol emissions over the US and potentially over Asia as well, which I would expect would have its biggest effect in that season because of the seasonality.
Suppressing the drizzle is what you're going to say, right?
Yeah, what's that?
Suppressing the drizzle then, right?
Right, and there have been downward trends in that since the 70s, just like you show in your North Atlantic. However, your North Atlantic box is a little in a slightly different location. It'd be real interesting to just, you know, you worry about subdividing the data too much. And while I certainly agree with that, here you have an opportunity for the most commonly observed, type in that season, in a season where you know that it's important. So it'd be really curious just to see if there's a relationship there.
That is a really good point. And again, that's one that I hadn't stopped to think about when I was digesting the data. That's definitely one that should be broken out, and the sampling should be good enough in the North Atlantic and North Pacific to be able to do that fairly easily.
Yeah, really cool. And I know climate models are suggesting that there is a aerosol-induced effect on precipitation in those regions.
Okay, that's good to know, and that's why I'm glad that we have some climate scientists who are looking at this stuff as well.
Cool work, Grant. I love seeing analysis of the raw obs. I'll speak up for Stefan Hassenrath in that. I'll take his place. I want.
All right. Well, thanks.
think I'm next.
Go ahead, John.
Yeah, Grant, great talk. That was really excellent. I echo everything everybody said before. As usual, you've taken a really insightful and creative way to dissect all manner of what seem like questions that are going to be impossible to answer. I thought it was great. I'm really intrigued, along with Liz and maybe everyone else. I'll go beyond just the North Atlantic storm track region, but also the North Pacific storm track region. Those are really coherent signals in the reduction of fraction of precipitation in a poleward of what I presume to be close to something like the climatological storm tracks. Now, the storm tracks vary from year to year to some degree, but if you had to lay them on top of each other over 5 decades, you'd probably end up having something close to those places, you know, right off the coast of Japan up to the Aleutians in the Pacific, and then from maritime Canada to, you know, the outer Hebrides of Scotland is a probably good, decent line to put that North Atlantic storm track. So I'm wondering if you had a really good point of supposition where you said, well, maybe it's just that the Arctic's warming up, and so, you know, convective showers will be reduced fractionally because the stability's not quite as low as it would have been otherwise with much colder air over the warm water. The other thing could be, and maybe you could tease it out, you could probably look at some measure of synoptic scale vertical motions at 700 millibars or something like that, and just see if those have also decreased. The fraction of positive or updrafts has decreased over the same period of time in roughly the same location, because that would perhaps tease out whether it's a synoptic scale change to you know, forced vertical motions, or whether it is in fact something more convective in nature. And I think there's a way you could probably do that.
Well, that's very interesting. Can you remind me whether, like, the NCEP analyses include vertical velocity as one of the fields?
Yeah, I was thinking of the Japanese reanalysis because it starts in 1958. That'd be a really good data set to use, and it certainly does have the vertical motion at a variety of different levels and at pretty decent resolution. And one could not only take the raw model output, but one could calculate the QG vertical motion to really make sure that you're talking about only synoptic scale vertical motions, and that and see if there's any trends. I mean, in a decrease in the synoptic scale or QG type vertical motions on the poleward side of the storm track line that we're talking about.
Well, that's very interesting.
Kind of interesting.
It would be, and I think in a way what we have are a couple of competing hypotheses. If we look, for example, off Japan and up into the Bering Strait, one hypothesis is that they're seeing a lot of aerosols from China and so on. They're suppressing drizzle, which is what Dan suggested. And the alternative is that it's a synoptic scale effect, which could be changing storm tracks or changing vertical motion. And it would be an interesting study to try to look at both of those hypotheses and see if they can even be distinguished for one. But I'd want to collaborate with somebody on either of those topics, so especially the synoptic stuff, because that's not my area. But I'm hopeful that this could be the starting point for possibly looking for some NSF funding or something to work with somebody, maybe working with Tristan with CloudSat to try to do that validation, maybe working with you on synoptic analysis that might dovetail with this work. But I think there's kind of a starting point here for looking at these questions in a deeper fashion.
Yeah, I'm definitely game. If you wanted to do that, I'd be game.
Good to know. Thank you.
So Grant, there's one more question from Noor in the chat, and then I think maybe we'll call it off. I have to set up a test with our speaker for Monday at 4 o'clock. So the question is,
that sounds good.
Is it possible to compare the SNOP data and satellite data and derive a more accurate pre-satellite era global precipitation?
That's a good question. Yes, I think that could be the case. It used to work the other way in that people were trying to use the ship reports to validate the satellite observations. But in the current era, the satellite observations are becoming more robust, especially with the advent of radar, whether it's the precipitation radar, the dual frequency precipitation radar on GPM, or whether it's CloudSat. The satellites are now probably able to do a better job of unambiguously determining whether or not precipitation is present than used to be the case. And yes, I think it might be possible to then calibrate the ship reports during the period of overlap, at least on like a monthly basis or a seasonal basis, and then see what happens if you go backwards in time and try to do the same thing. I think it's a very good point, and I hadn't thought of that, but I'm going to write that down as one more thing to think about. So I guess if that was the last question, I thank you very much for your attention and for the very good feedback at the end. And look forward to talking to some of you individually further as we try to explore some of these ideas.
Thanks, Grant. Great talk.
Thank you.
Yeah, thanks, Grant.